Hi, welcome back to the breadboard and another TI Tuesday. Why the sunglasses, you may ask? Well, today we're looking at a booster pack, which is an LED booster pack. And what makes this one particularly special is it uses a Launchpad C2000 Piccolo controller to drive 3 boost converters to generate a high enough voltage to drive a string of 8 RGB LEDs in series. And these things are pretty bright when they're on. Anyway, TI provided me the sunglasses to go along with the booster pack. I'm not saying you get them when you buy your own one, don't think that you do, but anyway, they are very bright. And one of the reasons why I wanted to look at this today is because in the last few weeks we've been looking at various current sensing chips and buck controllers where you have a higher voltage, say 12 or 24 or something like that, and you use a buck controller to drop those volts down to something like 5 or 3.3 depending on the situation and what you're trying to drive for that, what the supply needs are. In this situation, we're looking at a boost converter, which basically takes a lower voltage and converts it to a higher voltage so that it can drive loads that require more volts to be able to turn on. And in the case of a string of series RGB LEDs, we need at least 20 volts or so, because there's 8 of them, and typically it's sort of around 2 to 3 volts depending on the color of the LED. So we're going to look at this board now. We'll have a quick look on the computer of the topology, have a very brief discussion about what's going on. I don't want to make this all about the actual technology to do boost or buck conversion. We will do that in a future video though, but what I do want to do is show you what this board is, how it's put together, and how you could use it not just for this, but take the demonstration circuitry, because all of these booster packs and launch pads are about teaching you how to make your own products and educating you as to how this various technologies work and the techniques used to design your own systems. So without further ado, let me just turn this thing on. It's sitting right here. Right now I've got it turned off. It's powered up, but it's off. So I'm going to switch it to full brightness and you'll see what I mean. Alright, it comes up. I'm using a demonstration piece of software that you can download from TI for free when you and it will talk straight to the board. And you can see here the RGB LEDs have come completely on. We'll switch to the computer capture in a moment so that you can see better what's going on, but I can easily simply change colors here. There's a bit of a latency that's built in just for the fun of it to the program. So that was yellow, switched to orange, and it will slowly turn over a little period of time into orange. I can go to red, blue, green, etc. Or I can just pick my own colors if I want to. Anyway, we'll look at the program in just a moment, and but first what we'll do is we'll go to the computer capture and have a look at exactly what the circuit is and how Texas Instruments have tied a launch pad and a minimal amount of external circuitry to create this boost converter RGB controller. So what we're looking at here is the control suite. I've downloaded the latest version of Code Composer Studio, which is version 6.2, and I've also installed Control Suite, which comes with a lot of different applications, both to download into the launch pads and also to run on the local machine. What you see on the left here are the development tools for the C2000 launch pads, and the one that I've got selected here is the Boost XL C2K LED, which is the booster pack that I have with all those LEDs on. There are 2 demonstrations that are built into this. Now, one of them I can't show you because I don't have a capacitive touch booster pack to go on this. The other one is the PC GUI demo. So there are 2 parts to it. One is the Code Composer Studio project, and if I click that, it gives you instructions on how to get it installed into your computer for the Code Composer Studio to compile it and upload to the Launchpad. Not going to go into that. I've done a few projects in the past to show how to use Code Composer Studio, and I am planning on doing another one in the short future, which will show some of the things with the latest version, which has got a lot of new online features of Code Composer Studio 6.2. But for now, we're just looking at this Launchpad. So let's just pretend that I've compiled the demonstration application and uploaded it to the Launchpad. And now we're going to look here. We got a GUI application which you can launch right from within the Resource Explorer of Control Suite. So we'll just fire that up. And what you see here is the control panel to talk to the Launchpad, LED Launchpad. So the first thing we need to do is set up a connection to it. In my case, I've only got one thing plugged in, and it showed up on COM4, which is the C2000 Launchpad. It's a Launchpad XL TMS 2802X. So the first thing we do here is we pick COM4. We say OK, and then we hit connect, and we should get a greenish light here, which we do. And now we're able to talk to the control panel, the Launchpad. So you've got a set of preset colors here, and all you do, if you select one of these, it just sends the command to the code that's been put onto the Launchpad, and it sets it up with all the colors and everything else that you've picked. You can have it automatically run through the code, or you can literally just scroll these sliders up and vary the current that you want to each LED string. So you got a red, a green, and a blue. Now, the thing about LEDs, if you're not already aware about it, is that they are current devices, not voltage devices. When you buy the strings of LEDs from eBay or wherever else you may go, they have resistors in series typically that allow you to use them in a kind of voltage mode, but that's not really the right way that you're meant to drive LEDs. You're supposed to drive them with a constant current, and the current flowing through them, it has a direct correlation to the luminosity, the intensity of the light that they give out, not the voltage. So this is the way that we control them. Now, when we want to have a look at the schematics for this, and I'll bring up the schematic now for the Boosterpack. I'm not going to particularly show you the Launchpad right now, although I might have a quick look just to show you some of the pertinent features that are in there. But suffice to say that all of the electronics for pulse width modulation and everything else are all built into the Launchpad. And what the Boosterpack is providing is the inductors, diodes, FETs, etc. for the boost conversion part of this, the power stage. This is what the board looks like. I showed some pictures of this in a previous video because I had to change these connectors. These connectors here are actually the wrong ones for normal fit for a C2000. They should be pins, not sockets. So if you do buy one of these on its own without the matching Launchpad already fitted, then you may have to replace these connectors on here to the pin strips to make them compatible with your C2000. And that's something that I had to do. I made a video of that because I wanted to try out my new soldering station that I got from Weller and RS Components, and this allowed me to do that because I had to switch these around. But anyway, that's what the board looks like. We'll go into details of that in just a moment. It's, with the kit you get the LED Boosterpack itself, which is this board. You also get a 12 volt 1 amp power adapter, and that will be suitable for whatever country you're doing your ordering in. And if you open up the user guide down here, so we'll just open that up now, and scroll down a little bit just to have a look at the schematics of it. So here is the basic schematics of what we have, ignoring the fact that the Boosterpack has a 12 volt to 5 volt and 3.3 volt power supply built on as well. It's a buck converter so that you can use it to drive the onboard electronics as well as the launch pad that you may plug into it. I'm not using that for this example. But what matters here is that we have this box here, which is the launch pad itself. We've got the 32-bit processor. We've got a set of analog to digital converters running at 12 bits, and they can go up to 4.6 mega samples per second, which is pretty fast. And we also have 4 PWM outputs which go out to drive these various stages. Now we're only using 3 of them for this, but anyway, what we're interested here are the ones that are driving these 3 FETs here. Now there are some additional components in front of the FET, which is basically just a MOSFET driver, so that you can use a low 3.3 volt voltage coming out of a microcontroller and have it switch very cleanly and quickly a MOSFET for power control. So what we have here is we have the 12 volts DC that came out of the wall adapter, and then we have a coil, the inductors, there's one for each channel, and a fast diode, and then we feed into these LED strings. Now there are 8 LEDs in series here, and so that's going to be around 20 volts of biasing that you're going to need before these LED strings will be turning on. They might start to turn on around 18 or something like that, but they certainly wouldn't be turning on with just 12 volts. So what we need to do here is the microcontroller needs to input a pulse to these FETs to turn them on. What that will do is it'll start a current flowing through the inductors to ground. So if you leave it for an extended period, of course that current is going to go up quite considerably, because this is basically probably just not even an ohm. I haven't measured them, but they're not going to be very high resistance value from a DC perspective. But the minute you turn these MOSFETs on, there's going to be a magnetic field built up in here, and these inductors are going to resist the change in current, but that's going to just build up over a short period of time. Now what happens is, as soon as you turn this MOSFET off, these inductors want to keep that current flowing, so what they're going to do is push it through the diode to this smoothing capacitor and then onto these LEDs. And because the current is already flowing, the voltage will increase to the point where it will forward bias the fast switching diodes and actually provide current through here and through these LEDs. Now there's the exact same circuitry for each of these 3 strings, one red, one green, one blue, but at the bottom of each string as well there is a 100 milliohm resistor, which is a shunt resistor. This is where we get back to the current sensing that we've been looking at various topologies on other videos. And in this case, the current that is put across these resistors obviously is going to result in a voltage. So if you've got, say, 50 milliamps going through here, you're going to get about sort of 5 millivolts, because if these are only 0.1 ohms, you're going to get about 5 millivolts. Now this is being fed into a op-amp to amplify that signal, and then is being fed into the ADC of the launch pad. So there's one for each string that allows you to measure the current effectively going through the string, and we want to make sure that the average current is, say, 50 milliamps or whatever it might be that we set for each string. We also are able to measure the voltage on the top of each string, so that we don't provide too many volts going into the LED strings as well. So we have 3 voltage sensing points, which are also going to be through resistor divider networks fed into the ADC converter as well. Now one of the things that are in these Piccolo C2000 Launchpads within the CPU, it has a subsystem that allows it to read ADC values and drive PWMs and do a little bit of the logic completely autonomously of the main processor, which means that you could set this up effectively as a constant current power supply and then allow it to get on with things, while the higher level architecture of the processor can go off and do other things, which is really cool. And we've seen this in the previous video where we were looking at the C2000 based buck converter, where we were driving high current outputs on a board in very much the same way, but in that case it was a single channel and we had high side switching, and we were reducing the voltage down to sort of like 3 to 6 volts kind of area. Now in this case, of course, as I said, we're taking it from 12 volts and we're boosting it up to around about 20 volts. So that's kind of the other side of the coin when it comes to power management. Now, the fact that there are LEDs in these strings really is irrelevant to what the control system is doing. What we actually have here is a control loop, and if you know all three of them, and just focus on one of them for a moment, where we are monitoring a voltage to make sure it doesn't go beyond a certain threshold, which is set by the software, but we're also monitoring the current across the shunt resistor with an op-amp to boost it up to something that the ADC can read, to make sure that we don't exceed a certain amount of current as well. And the primary control for this particular circuit is going to be the current, because we are driving the LEDs, so that is what we want to be able to set as far as that's the managed parameter. And if we go back to this application that I was using a moment ago, you can see here each channel, the red, the green, the blue, it is the target current that we're setting. Down here we're sort of at a milliamp, and up here we can go up to about 50 milliamps. And you can just drive each string individually, or you can set for predefined ones, like that's blue, green, yellow, orange, red, etc. And it's just changing the current that's flowing to each of the strings so that we get the right colors. And what they've got here right now too is, as you can see, white for RGB LEDs is not all three LEDs with the same current. Because of the different voltage and intensities, the human eye, it's not, you don't want, and the output of each LED, you don't want them all to be the same to get a pure white. So you have to adjust the colors. And I'm not going to go into all of that now. That's a whole separate extensive topic of its own. But suffice to say that RGB for white is not just flat out of everything. You have to balance them properly. And then the same goes for each of the other colors as well. So this application is provided by Texas Instruments, and you can just run it simply yourself. And it's very easy to use. You can change the update rate here every 1.5 seconds to 2.5, 3. You can change the slew rate, which is basically how long it takes to drift from one set point color to the next one. And that's pretty much all it does. Everything else is all built into the underlying software, and the whole idea here is just to give you a taste of what you can do, and all of the source code for all of this is included in the download that you can get with the Co-Composer Studio and the Control Suite. So in here, all these downloads, you just bring them down, put them into your Co-Composer Studio, and then you can view them as much as you like. So what we've gone through here now is the basic circuitry of what is in here. Let me just bring up the actual schematic diagram for this so that you can have a better look. So the software is basically put into the, if you use all the default folders, which I would recommend normally, because everything that TI does with their software assumes a set of default folders, and if you start changing it, then you're going to have to be forever changing it. So if you go to C:/TI Control Suite, then go into development kits, then what you're looking for is the C2000 Launchpad. If you go into there, and then you've got the Boost XL LED hardware package, and in here there's actually a schematic as a PDF document that you can look at. All of the diagrams for to do your own boards are also in here, so you could actually have quite a kickstart to designing your own board if you wish. So let's just open this up, expand it out a little bit so that we can see it better. And just zoom in a touch. So make this full screen. So here is the main drive. So these PWM 2A, 1B, and 1A are coming straight from the Launchpad. And here's the little MOSFET drivers that I told you about. They provide up to about 4 amps of drive capability into a MOSFET. Each stage, there's one here, one here, one here. So you've got blue, the red, and the green. We'll just look at the green one for the moment. You can see here's our inductor, here's our 12 volt supply sitting here, and here's our MOSFET. So what will happen is the PWM controller from the microcontroller will tell this MOSFET to turn on. That'll start a current flowing through the inductor to ground, and then after a certain point the MOSFET will will be told to turn off by the microcontroller, but the inductor will want to keep that current flowing. So what will happen is it'll get pushed through this fast switching diode D2 here and charge this capacitor up, and the voltage here will basically get boosted up beyond the voltage here, because once the current is flowing, this is all inductor theory, basic electronics 101 kind of stuff, it'll want to keep flowing for a certain time until the magnetic field collapses. So by pulse width modulating this MOSFET, you can actually keep the current flowing through here, through the diode, and build the voltage up on here to the point where you will get to the desired measurement voltage you want. And what we've got here, I mentioned before that the microcontroller is measuring the voltage that's coming out of these boost converters, and what we have right here is this R11 and R13 where the voltage is being measured. There's a little basically a 5K and a 215 ohm resistor dropper network. So V green, which is the voltage going to the green string, goes back to the ADC so that it can be measured by the computer. And even though this might be 20 volts up here, because of this divider network, this is going to be a safe, 1 or 2 volts for the microcontroller to be able to measure it. And the same thing goes for the red and the blue channel. They're exactly the same. Now if we go down here and we look at the current sensing, we have a couple of dual op-amps here. These are the OPA 2350s. And if we just look at one channel, you've got the blue cathode, which these are the LED strings here. There's 8 per string. So you've got the anodes, which are being driven by the high side, so the output of this boost converter here is going to the anodes, 1 to each, and the bottom end of the strings, the cathodes, are coming into these current sense shunt resistors. So it's 100 milliohms, 0.1 ohms. There's one here, and one here. So you've got the red, the blue, and the green. And what we're doing is we're just measuring the current flowing through this 100 milliohm resistor. We're amplifying it because you've got a feedback of 1.91K and a 39 ohm resistor, so it's quite a high gain. I'm not going to try and calculate it off the top of my head, but basically this is going to amplify that signal, and the I blue here is going to feed to the ADC input of the microcontroller. Now this next part here is just the basic power supply that's built onto the board that I had mentioned. So we have a little buck controller that'll take the 12 volts coming in from the adapter, and it's creating a 5 volt supply for use inside. And then there's a little linear regulator here that drops that down to 3.3 volts for where it's needed as well. So this board could supply the booster pack if you wanted it to. If you set it up to run completely standalone, it would all work that way. But let's go down a bit further where we look at the connectors now. We're going to ignore this little bit here. This is if you're using a touch controller. There's actually a complete MSP 430 microcontroller built onto the booster pack as well, solely for the purposes in this case of interfacing with a capacitive touch controller board that can be used with the other demo to control the RGB LEDs as well. I don't have that board, so we're just going to ignore this for the moment, but suffice to say that it's a good example of how you can very easily use a very low cost microcontroller to create a simple user interface when you want to. Now, going back to the other part of the circuitry, you can see here we've got the PWM outputs that will go to each of those MOSFETs, and we have all of these analog channels coming back in, both for the voltages and for the current measurements, so that we can manage the switching of these regulators up here, these boost regulators, not those ones, these ones here. And that's pretty much the way it works. It's not, as I said, I'm not trying to get into how buck boost converters work or anything else, but this board is just a very good example of where you can take everything we've been looking at over the last few weeks for regulators, for current shunt measurement, for buck converters in this case, but we've changed. This is changing the topology slightly, and we're boosting the current instead of dropping the current. to a higher value for LED strings, but the principles of operation are pretty much the same. We have a pulse width modulated signal feeding into some FETs that are controlling the current flowing through an inductor. That output is being smoothed and then fed to a load of some sort. In our case, this load is a set of RGB LEDs, and then the low end of those LEDs have current shunt monitoring that is then feeding back into the ADC inputs of this microcontroller. Now in this case, the microcontroller is more than capable of reading all of those LED channels and converting the signals into something that can be used quite easily by the code that's in there. If you were using a different microcontroller that didn't have that capability, you would probably need to use the INA 301 or one of those other current shunt current monitoring kind of chips where they have the built-in amplifier and everything else in the chip. In this case, we don't need that because it's all built onto the board here and built into the C2000 Piccolo microcontroller that we're using. So anyway, you can see now that this is a great little board to learn how to do RGB constant current controllers. You know, in this board's case, we've got 8 little RGB 50/50 LEDs in there, but this could easily be a string of hundreds of RGB LEDs with a 60-volt string, you know, or driving hundreds of watts of power. Or you would be really changing, the control circuitry would be pretty much identical. You would probably just have a different inductor and a different FET and smoothing and things, but that would be pretty much it. Everything else would be the same, and it would be an easy matter to scale this up to something really, really cool, either for a home, for an entertainment situation, or you know, maybe photography where you wanted to be able to select very close color combinations and things with a light meter or a spectrum analyzer, color spectrum analyzer, that is. But it's a nice little booster pack that allows you to learn a lot about how to do LED power control, and even forgetting the LED part, a very simple modification to the software would allow you to run this as a boost converter based on voltage control instead of current control and things like that. So I think it's definitely worthwhile studying this, and in another video I think what I'm going to do is actually get the oscilloscope hooked up so that we can have a look at the actual waveforms. What I'll do is I'll line up a traditional buck converter or maybe a boost converter, and also connect up the software driven buck and boost converters and drive these things, and maybe we can even hook up a arbitrary waveform generator, just unplug the Launchpad completely and just drive the input to these stages with a PWM from a signal generator, so that we can actually get down to basics of how this circuitry works. And I can do the same thing for the buck converter that we were looking at a few weeks ago, because it's basically working in the exact same way. It's just reducing the voltage but at high efficiency instead of increasing the voltage with a high efficiency. Because we're using an inductor, we're basically doing a power conversion. So if your load is, say, 1 watt, then you're only going to be drawing about 1 watt from the wall adapter as well, less the the losses. So if it's only, say, 90% efficient, then you might be drawing, you know, 1.1 watts from the wall to deliver about 1 watt or just under 1 watt to the load. But either way, by using buck and boost converters, you can get some very, very efficient power conversion techniques, and enable yourself to create some LED lighting solutions or other power solutions that are efficient, that can tolerate quite a wide range of input voltage swings. And you can combine a buck converter and a boost converter so that you can actually automatically switch between the two, even if you had to, as the voltages, maybe it's in a battery system, go up and down. Anyway, I'm starting to digress here, so I just wanted to introduce you to the LED boost converter and power board, the booster pack, and I've done that. And if you're interested, I will provide links in the post so that you can go to the TI website and have a look for yourself and buy one if you want to, etc. Anyway, so that's the overview of the LED booster pack using a Piccolo C2000 Launchpad to drive it. If you like it, great. If you don't, well, sorry about that, but it's going up anyway. And next week I'll have something else for you. So till then, happy Tuesday. Bye.